due to save money. Yes. 1, 2, 1, 2, recall how the quantum product is defined if Pi is a basis of H star XZ X homogeneous. And G in J is equal to the degree of Pi J and G I J. Okay, maybe it's better to invert this. Okay. P sum Okay. This is just a quick recall of how the quantum product is defined. So let's recall this is a basis of H star X Z, where X is homogeneous. We form the matrix given by the degree of the intersection, but we are more interested to its inverse. Phi is defined as this formal polynomial, formal power series in these variables. And finally, the quantum product is defined linearly with respect to this ring here. This the derivative of. Okay. Now we want to prove that this is associative. So Pi J Okay. Okay, this equation is equivalent to okay. This will be just a sketch of the proof. I will not write all the details, all the combinatorial details. I just focus more on the ideas. Okay, this is equivalent doing the multiplication to this. Okay, maybe it's better to be sure, but it should be tough. Okay, maybe there is some confusion here. But anyway, if we substitute this inside this and using linearity, we perform all this product, we got something like this condition that is actually is a differential equation. Differential equation of V of degree 3 in its partial derivatives, and this differential equation is called UDVV.
Witten digraph Berlin.
Witten digraph Berlin. Okay. I call this F E J K I. Okay. KT. Okay, because
I'm standing.
this must be true for each T. Okay, E, J, L, F, and T are all indexed between 1 and N. So maybe it's better T, J, K, L, and T belongs to 1 to N. So we have a sum between among L and F, both sides. And this must be true for each t. Okay. Okay, this is equivalent. Okay, so we have to prove that Fj kt is equal to F jk. Okay. Let's just let me check. Just want to be precise. So, and GLF, F, A. Okay, P. This is correct. LF, J, K.
Yeah, it's good. It's fine. Yeah.
J. This is E.
F.
F.
L.
E, F, P. Okay.
Yeah, it's fine.
It's this one.
Because you can always change the.
Yes. Because here in the Fulton Pandaribande article, they use E and L, but I confuse them, so I changed it. I prefer to use T.
Yeah.
So it's this one. So, and this is, if I call this, depending on E, on I, J, K, and T. Following this notation, this is J, K, I, T.
Yeah.
So we have to prove that these are equal. Sorry for today. Okay. Let's rewrite this in the following form. Ij kt is equal to B1, B2, LF, N1, N2, equal 0, of what? Okay, this is we introduced this notation last time, so don't let me rewrite again. F, LF, times theta 2 gamma H2 okay here. Okay. It's a long product, so this is here and this is here. Okay. Okay. We need a lemma. So I will write it here. No fixing. Okay, these are the boundary divisors, okay, which we did in the second lecture. So the sum is all we are closer to what we want to prove. So, let's fix n greater or equal than 4, 4 integer greater than n. And let's go. And we define this quantity that is a divisor in the moduli space m bar x by theta with n marks, and it is a sum of boundary divisors. Which boundary divisor? This sum is over all partition. So A and B are subset of 1n. So it's a partition, so it's a disjoint union. Where I and J are in this set. Are in A. K and T are also in this set, and they stay in B. Beta 1, beta 2 are two effective classes such that the sum is beta, which we fix. And this is the boundary divisor defined by this information. And the proof, we just give an idea of the proof. Consider this map we saw in the first lecture is the map that, given a stable map, gives a stable map to its domain. Forget n bar 0, 4, but this n bar 0, 4 is which index are forgotten. The index different from this 4. So this is M0, and here I write explicitly the marks which I keep: I, J, K, T. And this is what to put in 1. Okay, so I forgot all the marks except this one. So Dij kt is the inverse of the point representing. I need this space, so I hope you already wrote this one because I need it. So this is a point of this P1, of this M04, and it's the point exactly where I and J are in the same component, and KT are in the same component, and we have a component connecting these two components. So Dij IT is the inverse of the point representing JK IT. Why? Okay, because here we have stable maps here, but I and J are in the same component, in the same part of the divisor, and K and T are in the other part. So maps here looks like something like that, more or less. But we forgot the maps to X. We forgot all the other maps. We just keep this. And under this map, these and these are the pullbacks of this point. But two points, P1 are linear equivalent. So this point are linear equivalent. This is equality modulo linear equivalence. They are linearly equivalent. This means equality. Equality in the peak. The peaker group. Since the points of P1 are linearly equivalent. So Dij kt and Dij IT are yeah, maybe should say that this is true because these maps are flat. Because in general, the pullback of two linearly equivalent points is not linearly equivalent if the map is not flat. But this is a composition of flat maps. So this is true in this case. This is the first lemma. Second lemma. Let B do you recall that this is equal to a fiber product of this, that is the max in beta plus 1, these that are x beta 1, these that are the marks of A plus 1, and we perform a fiber product with respect to the evaluation of this additional point. So we construct a diagram. X beta. This is the inclusion here. And this is the diagonal inclusion. This is the diagonal inclusion. This is important. This is a fiber product with respect to the evaluation that point. Okay. What I'm doing here, I have the evaluation maps, but I have n evaluation maps, one for each market point. So I can construct the fiber product of all n evaluation maps, and these maps to x times x times x, x12. Okay. Here, I have also n evaluation maps because I still have the evaluation maps here and the evaluation maps here. But I have one additional maps. But remember that here, this is constructed by this product, by the product of this one, which respect to the evaluation of this. So the evaluation of these marks and these marks here coincide. So I have n plus 1 evaluation marks. So LV1, LVN, and AV at evaluation maps. Evaluation map. So it's n plus 1. Here, a stable map here and the stable map here, they have both an additional mark, but the evaluation of here and here does not coincide because they coincide here. In general, they outside B, they don't coincide. So I have again a product of evaluation maps for n plus 2. Okay. Well, the last two are the evaluation of the point in A, and the second, the second last is the evaluation of the point in A, and the last is the evaluation of the point of B, of the additional point of B. So this is the evaluation of this point. So I have an inclusion here, and this is tautological this fiber product. And here I have a map attached for God last map, last point. I construct this diagram, and what I want to prove is that then P lower star of alpha upper star AB star 1 gamma 1 star So where gamma 1 and gamma n are cohomology class in X, and this is a product in M bar, which I pull back to D, and which I push forward to this. So this is equal to F. Okay. We skip the proof of this lemma because it's just a manipulation of cohomology class inside this commutative diagram. So we leave this as exercise, but it's not so deep. There is no so many ideas here. It's just you start from this, and you use the commutativity to pass from here to this. So proof, it follows from the commutativity of the diagram, and we skip the proof. Okay. So let's finish the proof of the main theorem that we want to prove. This proof is just to give you an idea of how to work with this stuff. We don't engage in a complicated computation that are not have no deep idea inside. So let us define G F S E again, where the sum is over all partitions such that Q and L are in A, S and T are in B, and over beta 1, beta 2, let's do X beta, such that beta 1 plus beta 2 and F. Okay. By lemma 2, G to F S T 1. Okay. Here we use lemma 2, the lemma we write on the left side of the board, and we deduce that this expression is exactly this sum. Again, we don't write details since they are just normal computation, normal manipulation, not so deep. And so by lemma 2 we have this equality, and by lemma 1 by lemma 1 we deduce this equality. That if you remember, lemma 1 was just an equality between the sum of boundary divisors. Since we are integrating boundary divisor, it follows this equality. Again, by combinatorial remarks, which we skip because it follows. F I I just wanted to give you the main idea of the proof, because the proof is long, full of computation, but it's important because this is the only property of the quantum product which is not easy. I mean, commutativity and neutral element and so on, these are almost immediate. This is not trivial, so we have to prove, and we use it González money. Okay. If there are no questions, I will give you some examples. Questions? I don't know if there are no questions because I'm too much clear. Okay, let's give some explicit computation. Okay, let's start with the most easy example. X equal to P1. Okay. So H star of P1 is generated by two classes, T1 and T2. Where T1 is the class of P1 and T2 is the class of a poly. Let's compute phi. So I recall you that phi is the sum. It's common when X is a projective space. Instead of write beta, to write D in the sense that we mean the degree of the map. Because, beta is always D times the class of a line. So instead of write beta, we write just D. So here we wrote the sum among all beta, so we write from D from 0 to infinity, because D can be any non-negative integer number. So this is equivalent to this. What? N bar 0n P1 D AD star T1. Okay, this AD star here we have n market points, so we have n evaluation maps. And I mean that this is n1 times AD star T2, and this n2 times. N1 plus N2 is equal to 1. This Y1 divided to N1 factorial, N2 N2 N2.
N1 plus N2 equals 3, equals N.
Yes. Okay, let's compute explicitly this object. When D is equal to 0, do you remember when in the first lecture, when beta is equal to 0, we know that the integral of any Gromov-Witten invariant is 0 if n is different from 3. So one 0. This is equal 0 if n is different from 3. So let's compute here P1 0, AB1 star 1, AB2 star 1, AB star 2. Okay, this is when D is equal to 0, this is the only non-zero Gromov-Witten invariant, because if we have it's very simple. I mean, this is the degree in P1 of P1 times P1 times P2, and this is 1. Because this is all X, all P1. All P1 a point. So the degree is 1. If one of these is any other different combination, always gives 0. If I have here T2 more than 1 time, it's 0. If I have 0 times T1 times T1 times T1, which is of degree 0 because it's not a 0 sign. It's the only non-zero integral. So it's 1. Not that this can be in the third mark, it can be also in the second, and it can be in the first. So I have 3 Gromov-Witten invariants of this type. So if D is equal to 0, what I have T1, T2. So epsilon1, epsilon2 divided by n factorial, which is 3 factorial. But I have 3 possible combinations. So this is multiplied by 3. Time plus so I computed the part where D is equal to 0, and it is this one. So this is epsilon1 squared, epsilon2 over 2. This is called the classical part of the quantum potential because it doesn't depend on this moduli space. Depends only on X. So plus this one. Okay, so let's compute that. Now, when D is equal to 0, any Gromov-Witten invariant is 0 if T1 appears. This is also a property we saw in the first day. If here, when D is equal to 0, this one we have at least one T1, all the Gromov-Witten invariant is 0. So this is the only, the product of this is the only that is candidate to not be 0. Because I cannot have the T1. So I need only T2. But we can say something more. So we know that this is 0 if this condition is not satisfied. But the codimension of T2 is 1 because of a point in P1. N times is n, so n times 1. This must be equal to the dimension of this space, which is minus kx, which is 2 times d, plus the dimension of x, that's 1, plus the number of market points, minus 3. So, in order to have this equality, d must be 1. So, this is 0 if d is equal to 1, is greater than 1. So, we have another simplification. So, let's compute this. Now we use another property of Gromov-Witten invariant. Let's say that if one of the cohomology cluster here is a divisor, I can put it outside the integral. So this I can put this outside the integral, which means beta. Beta is so the class of the line times the Gromov-Witten invariant without this. And this is 1. Because it's the degree of a point. So this is 1 times this. I can continue. So this is 1. Yes. And so okay, when d is equal to 0, this is it. 2 plus this doesn't appear. I have only epsilon 2. When d is equal to 1, so this is solved. The Gromov-Witten invariant is 1 times epsilon 1. Does it appear familiar? Okay, the exponential starting from 3. So technically it's this minus the first, the second, minus the third. Okay, now to compute the product, we need the third derivative of this object. So let's start, for example, by this. If I derive 3 times with respect to epsilon 2. This is in epsilon 2 is of degree 1, so disappear. This part disappear also. So we just yeah, it's strange to use the exponential, the analysis function, but this for us is just a formal power series. It's not important that it's also convergent. For us, it's a power series. So it's just an easy way to indicate this power series. Okay, this is one first year calculus. And for example, if I want to compute 2 to 1, so I derive with respect to epsilon 1. So this part disappears. And I derive 2 times with respect to epsilon 2. So also this part disappears. So this is 0. Okay. Let's compute this. Who is G? And who is this matrix? Is the matrix obtained how? P1, 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 P2, P2, P1, P2, P2. This is not a 0 cycles. This is 1, 1. But here, is the inverse of this one, which is the same. So this is okay. So this is not 0, only in the case G to 1 and G 1 2. So 2 2 2. G to 1 P1 yes 2 to 1 G 1 2. But this is 0 and this is X. This is 1. Exercise.
What is the exponential of what? What is the variable? Yes. 2, 2, 1. Yeah.
Okay, so we compute the quantum product of T2 times T2, and it's this one. You can compute this one, very easy. So, the quantum product, the quantum cohomology of P1, which is indicated Q of P1, is, so I have epsilon 1 and epsilon 2. Okay. I also have T1, but T1 is the identity, so it's 1. So I don't write it. It's included in Q, and I have another variable that is T2, with the condition that T2 times T2 is equal to A divided. This is the quantum product of P. Okay. I mean, this star just to be consistent with what with the notation we use up to now. But I could have written this P2 square equal to this, because we don't have anymore a product of theory. And this, it doesn't exist here. Okay, so this is also a perfectly possible way to write this concept. Okay. Okay, this is times T1, but T1 is 1. Okay. If there are no other questions, let's see a more interesting example. That is the example the natural example we here. Picture. The idea involved are quite the same. So maybe since time is running out, I just give you the only interest of P2 is okay. Why? Because if you have T1, then it's automatically 0. Except in the case D equal to 0, but it is also not so interesting. If you have a line, we can use the fact that this is a divisor, so we can put it outside. So if we have T1 is 0, if we have T2, we can put outside of the integral, and at the very end we just have Gromov-Witten invariant involving only T3, and in that case we use the fact that if n is different from this number, then the integral is automatically 0 for dimensional. But this is only the only interesting thing. It follows which I leave you as an exercise. That P of P2 is epsilon1 squared epsilon3 over 2 plus epsilon1 epsilon2 squared over 2. This is the part where D is equal to 0 plus the part where D is not 0. And when D is not 0, n depends on D by this formula. So I can get rid of n. Again, it appears an exponential, but we know it's perfectly fine because it's a formal polynomial as any other else. To simplify computation, I write this gamma epsilon3. So phi is square epsilon3 over 2 plus epsilon1 over 2 plus.
So is there a formula for the ND?
Sorry?
Is there a formula for the ND? It's a rational number, yes.
This?
Yeah.
Actually, this is also always integer. Because this has a numerative meaning, and we will see this later. Okay? This is an integer. It's not only rational. It's actually an integer. We still have not discussed the numerative meanings of this number. Okay, I leave this as an exercise. I leave you as an exercise to compute all the quantum ring of P2. I give you just an example. This product here becomes T3 plus gamma 2 T2 plus gamma 2 should be times. This is an example of how this works. But we have associativity. Just a remark, Okay, this is the only interesting Gromov-Witten invariant, but I still don't know who it is. So this is I know just that it's a rational number, but I don't know who it is. I can compute for d equal to 1, to d equal to 2, to d equal to 3, but I don't know all of them. They're just the numbers. Okay? So we have associativity. So T2 times T2 times T3 equal to T2 times T3 times T3. Now, this is true if only I start to computing explicitly this equation, and I can find that this is true if only gamma 2 is equal to gamma 1 square minus gamma 1 times gamma 1 2. This is the derivative, like in the case of phi. So I simplified from a condition of phi to a condition of gamma, but gamma is this expression. So I can make the usual algebraic manipulation, and this is true only if ND satisfies this historical equation. Okay, so this is satisfied only if this is satisfied, which is true if only this is satisfied. I am being clearly positive. And so to compute this, we just need the first one because it's recursive. And the first one is 1. Okay? So this is the first time out this ND was computed for every D. This ND is this one. So it's the integral computing in some sense maps which 2 marks such that the image is aligned and the 2 marker points, the image of the 2 marker points is 2 fixed points. Actually, to compute these, there are a lot of methods, but this is not the Grassmann. So let's say that I finish here, and I just give you a couple of remarks, which is the first one is artist number enumerative, and take count, so enumerative. numeral. And the answer, this means that ND, or Gromov-Witten in general, is equal to the actual number of curves of degree V passing through
3v minus 1.
3D minus 1 points.
General position.
General position. Look that this is not obvious because, as I said in one of the first lectures, these Gromov-Witten invariants are among a moduli space of maps, not of curves of P2. And this is quite different. But the answer is yes. So N1 is the number of lines because of degree 1 through general point, which the answer is always 1. So we know that is 1, and we can complete all of ND, and we know that ND are enumerative. Yeah, but how do you prove this? You prove this in general. You have a Gromov-Witten invariant over a homogeneous variety. There is a theorem by Kleiman, which is called a Kleiman-Bertini theorem. Let's say that if G have an action of X, I avoid to say this theorem because it's quite complicated, but Kleiman-Bertini, you need that G act on X transitively. Transitive action of G on X, and in our case, where G is an algebraic group, in our case, X is G over P. So we have a G acting on X as we want. And this allows us, suppose the gamma 1 is the class of subvariety big gamma 1, and so for all other index exists. By the Kleiman-Bertini exists G in big G such that A star 1 G gamma 1 schematic intersection A star N G gamma N. This is reduced zero cycle supported in N. So, when we have an action, a transitive action of G over X, for example, when X is a homogeneous variety, then if I have a Gromov-Witten invariant like this, I can find a G, an element of the group, such that this schematic intersection is reduced, is at zero cycles, reduced, if the dimension is correct. And it is supported in the part of the moduli space where the domain of the maps is irreducible and we have no automorphism. And maps here are the type of maps we like because they are unequally defined by their image. So this Gromov-Witten invariant, multiplied by G, leaves the cohomology class equivalent. So this doesn't change the cohomology class. So there is no difference if I put it G. This leaves the same. And this count maps touching the gamma I and maps here. So this implies that it's an inverse. So what happens when this is not true? When we have maps with space without that condition. In that case, the Gromov-Witten invariants are not enumerative. And the problem of understanding if it's enumerative or not is quite difficult. In general, it is difficult. Okay. Last remark. It's just a remark on the part that we couldn't cover, which is the concept CT about formula. Step following. Let C star n plus 1. This torus be acting on Pn. So we have n plus 1 dimensional torus acting on Pn. By composition, this action gives and that for every D with acting on Pn with only n plus 1 fixed points. It's a finite number of fixed nodes. F1. Okay, I have no time to explain this, but this formula allows us to compute Gromov-Witten invariant. Very explicitly, with a sum among all the fixed logic of the quotient of two polynomials, where P and Q are polynomials with n plus 1 variables, which and P and Q depend on F1 and on the action T over I mean, if I change the action, these polynomials in general can change. So this this formula allows us to compute a lot of Gromov-Witten invariants. So I could use to compute this? Yes, I can. But the recursive formula is clearly better because this allows us to compute one Gromov-Witten each time with a very complicated sum, and that is recursive. It's very fast. But this works in more general situation. For example, this works also here, where I have a chain class of a vector 1, where E is a vector 1. So here I cannot use the recursive, doesn't make sense, but I can compute this one using this formula, and it works more or less this. So I think I stop here.
Okay, thanks. There is one question by one person in the audience, which is, can you please refer to some places where I can find how to compute psi classes for tangent point class with the correct point insertion?
Where I compute?
Where I compute psi class for tangent line class with correct point insertion on M bar G1 P2D. So tangent line class. So I guess it is a
okay.
It is a class of tangent line bundle and the point insertion.
So I think it means integral like this.
Yes, sure. It's C1 of L star.
GN?
Yeah. Thanks. Maybe you can say the complete question.
Yes, yes. So to make sense, you need one mark point and intersecting some other point classes.
C1, C2, something like this?
Only one psi class, and other things are just point classes.
Only one, and then?
Yeah, F2 star point.
X is what?
P2.
X is P2.
P2 degree D.
Which was degree D.
Yeah.
And G is positive?
G is positive.
N is 1.
G is positive.
So there is a program called GrowI, but I'm not sure.
Yeah, so I guess the problem is that G is positive, but we didn't know anything.
Yeah, we didn't cover this because, as I said in the beginning, the positive genus is more complicated, and this is a basic course. I even had time to cover the psi classes in the case 0.
Right.
But but you are asking for a reference, no?
Yes.
Okay. In this moment I don't remember, but and that's the positive genus case is not the case where I'm more comfortable. But I suggest you to check the book from Ori, and then Kande, Vakil, and so on. And the name is mirror symmetry.
Okay. Thank you.
I mean, it's in the bibliography of this course. Did you check this? Do you know this book?
Okay.
Yeah, I know this book. I haven't checked it. Thanks.